Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be completing the definitions of book 7, of Euclid's Elements. So let's begin. Now, definition 16 is the next definition, and it states that when two numbers are multiplied, in other words, when we take the product of two numbers, such a number is called a plane. Okay, a plane number. So an area is generally defined as the product of two arithmetic means. I was the first to realize this in human history. Did the ancient Greeks know this? It's possible that they did not know because there is no formal definition of the arithmetic mean in any of the known Greek texts. And when I say no formal, I mean no valid, no formal valid definition. Because, I mean, if you take a look at what Aristotle did, it's pathetic. And Aristotle was no mathematician at all. He was more of a philosopher and a logician. So, anyway, there was no worthy definition that proves that they did understand or did have a knowledge of the arithmetic mean and exactly what it means. And there's no other recording, to my knowledge, except Aristotle's and one particular place in the Elements. And I think that's about all, in my opinion. I do have an article about this on academia.edu, so I'm not going to spend time on it. It also appears that Euclid didn't think it important enough to produce a formal definition, and yet the reason calculus works is due to an arithmetic mean. Okay, in other words, you can actually, which, by the way, that's what the mean value theorem is about, and I also was the first to understand that. So the mean value theorem tells us that you can find the arithmetic mean of all the y-ordinates of a curve in a certain bounded interval, and there are innumerably many of them, in a fixed number of steps. That's what the mean value theorem tells us. That's the amazing thing about the mean value theorem. It's about a telescoping sum which produces an arithmetic mean. On the other hand, the above definition, which Euclid stated, holds for any area, whether it's a plane or a curved surface or any other particular surface imaginable. So, from that point of view, it's pretty sound. Now, definition 17 is about a solid number. And if you hadn't guessed it yet, volume is generally defined as a product of three arithmetic means, and it holds for any type of volume or solid. Okay? So, definition 18 talks about a square number. Now that's a number that is multiplied by itself. Okay, so notice that in this definition, Euclid is talking only about numbers, not magnitudes of all types, because I mean, not all magnitudes are measurable. So, for example, in book 10, Euclid deals with squares that have no common measure. So, a square with a side of a half has no measurable area. Okay, you can approximate it, but it doesn't have a set measure. And that's what it means to be a number, by the way. You can't say a number is a name given to the measure of a measure that approximately describes a magnitude of size, like the absolute morons of mainstream academia are indoctrinated and brainwashed to believe. That's not the case, okay? And this also prohibits any magnitude, such as a square root of a negative number, because in order to determine a square, the number must have the same sign, okay? So you can't say, all right, let's take the square root of a negative number, because what would the sign be in that case? Would it be something in between minus and plus? There are only two signs, minus and plus, okay? Now, Euclid didn't mention negative numbers because, frankly, there's no need for them in mathematics, despite their invaluable usefulness. And they do make mathematics a lot easier. And also, let's not forget the invaluable usefulness of 0 as a pretend number and a placeholder, just so that we don't offend the feelings of those people who believe in their ignorance that 0 is a number. Definition 19 seems to be somewhat redundant to me because it's almost identical. It is identical to definition 17, with a condition that the sides of the object in definition 17 are all equal. So it also makes me doubt that Euclid actually understood the concept of arithmetic mean, or even if he had any notion of the general formulas for area and volume which I introduced 2,400 years later. Definition 20 says that numbers are proportional when the first is the same multiple of the same part or the same parts of the second and third. So here Euclid gives a more formal definition of the equality between fractions of numbers that are proportional. Now contrast this with geometric arithmetic in Book 5, where ratios can be proportional without being equal. Okay, this is not possible in algebra, because a half is always equal to 2/4 in algebra. Why? Because all numbers in algebra are formed from the abstract unit, so they don't have different units. Okay? Definition 21 says that similar plane and solid numbers are those having proportional sides. So let's do an example with a plane number, which is given with sides 54 and 24 that have the proportion for 4/9, and they also have a proportion between their factors. So, for example, if we choose the factors 18 and 9 for 54 and 12 and 6 for 24, then the factors have the proportion 2/3. Now notice 2/3 is not in proportion with 4/9. Okay, and the above example also applies to solid numbers with respect to factors, and I leave this as an exercise. Finally, the last definition says a perfect number is that which is equal to its own parts. That's not quite correct. A perfect number has factors whose sum is the number itself. Okay, and I've given you 2 examples, and there are many others. I don't need to go into that. And this definition is used later, so it's an important definition. Now, in the next video, or one of the videos that I shall be producing in the future, will be on the propositions. Okay, so I'll also do the propositions of Book 7. If you're not already a subscriber, please become one. Click like on my channel. I do have many enemies in the mainstream. If you send me a request, I will give you access to three special folders on my drive, which are on my articles, my LinkedIn articles, and applets, which you can use in your teaching or in your learning. I'm John Gabriel, and this is the New Calculus Channel. Until next time, goodbye.